The tropical sun beat down mercilessly on the remote airstrip in the Solomon Islands. It was late 1943, and the tide of war in the Pacific was beginning to turn. Among the wreckage of yet another fierce aerial engagement, Japanese recovery teams moved carefully through the debris, searching for anything that might give their struggling war machine an edge. What they found that day would shake the very foundation of Japanese aeronautical engineering and reveal a technological gap that was far wider than anyone in Tokyo had dared to imagine. The aircraft lay crumpled at the edge of the jungle, its distinctive gull wings broken but still recognizable. It was an F-4U Corsair, one of America's newest and most formidable fighters. The pilot had not survived the forced landing, but incredibly the massive Pratt & Whitney R2800 double wasp engine remained largely intact. For the Japanese engineers who would soon examine this mechanical marvel, it represented both a treasure trove of knowledge and a sobering reality check. This is the story of what happened when Japanese technical experts came face to face with American engineering excellence. It is a tale of ingenuity confronting ingenuity, of pride meeting humility, and of brilliant minds grappling with the realization that their nation's industrial capacity had fallen dangerously behind that of their enemy. But more than that, it is a story about the brutal calculus of technological warfare and the men who dedicated their lives to understanding the machines that would determine the outcome of the greatest conflict the world had ever seen. The Pacific War had been raging for nearly 2 years when this particular Corsair fell from the sky. The early days of Japanese air superiority were long gone. Pilots who had once dominated the skies in their nimble Zeros now found themselves facing increasingly sophisticated American aircraft that could outperform their fighters in nearly every category. The men in Tokyo's aeronautical research facilities knew something was wrong, but they didn't yet understand the full extent of the problem. That understanding would come piece by carefully examined piece as they dismantled the Corsair's engine. The recovery operation itself was a testament to how desperately Japan needed technological intelligence. Under the cover of darkness, a specialized team worked to extract the engine from the crashed Corsair. These were not ordinary soldiers, but technical specialists who understood the value of what they were retrieving. They worked with painstaking care, knowing that every component, every design feature, every manufacturing technique held potential lesson. The engine, weighing over a ton, was carefully crated and prepared for the long journey back to the Japanese mainland. The journey from the Solomon Islands to Japan was fraught with danger. American submarines prowled the shipping lanes, and Allied aircraft controlled much of the sky. The precious cargo had to be transferred between vessels multiple times, moving through a network of increasingly precarious supply routes. Each transfer risked damage to the delicate internal components that the engineers so desperately wanted to study. But somehow, against considerable odds, the engine arrived safely at the Nakajima Aircraft Company's research facility outside Tokyo. It was a cold morning in early 1944 when senior engineer Takashi Yamamoto first laid eyes on the American engine. Yamamoto was one of Japan's most respected aeronautical engineers, a man who had dedicated his entire career to perfecting the internal combustion engines that powered his nation's warbirds. He had designed components for the Sakai engine that powered the Zero, and he took pride in the elegant simplicity and lightweight of Japanese aviation engineering. He approached the American engine with a mixture of curiosity and, if he was honest with himself, a certain condescension. How much could he really learn from these Americans who had only recently entered the field of high-performance aviation? That condescension would not survive the first day of examination. The R2800 Double Wasp sat on the examination stand like a mechanical monument to industrial might. Even before they began the detailed teardown, its sheer size was impressive. It was an 18-cylinder, 2-row radial engine that displaced 2,804 cubic inches and produced over 2,000 horsepower. By comparison, the most powerful Japanese engines in service were producing barely 1,500 horsepower, and even those were proving difficult to manufacture reliably. But size alone did not tell the whole story. What mattered was what lay beneath the cowling. Yamamoto assembled his team of 12 senior engineers and technicians. These were men who had spent years designing, building, and refining aircraft engines. They understood metallurgy, thermodynamics, and the complex interplay of forces within a high-performance power plant. They gathered around the American engine with notebooks in hand, ready to document every detail. What they were about to discover would fill those notebooks with revelations that would fundamentally challenge their understanding of what was possible in aviation engineering. The disassembly began methodically. Each bolt was carefully removed, each component photographed and measured. The Japanese engineers worked with the precision of surgeons, knowing that they might never get another opportunity like this. As the outer casings came off and the internal mechanisms were revealed, a palpable sense of unease began to settle over the research facility. The first shock came from the quality of the materials. Yamamoto picked up one of the cylinder heads and felt its weight. The metal was denser, stronger than anything they were using in Japanese engines. It was a specialized alloy, clearly designed to withstand extreme temperatures and pressures. He called over his metallurgist, a brilliant young man named Kenji Sato, who had studied at Tokyo Imperial University. Sato examined the component under magnification, took hardness measurements, and ran preliminary chemical tests. What he found troubled him deeply. The Americans were using advanced alloys that Japanese industry simply could not replicate. These weren't just marginally better materials. They represented a fundamental difference in industrial capacity and metallurgical knowledge. The alloys contained rare elements in precise proportions, achieved through sophisticated refining processes that Japan's overstretched industrial base could not match. Even if they could identify the exact composition, which would take months of analysis, they lacked the industrial infrastructure to produce these materials in quantity. But the materials were just the beginning. As the team delved deeper into the engine's construction, they encountered manufacturing techniques that seemed to come from a different era of industrial development. The precision of the machining was extraordinary. Tolerances that Japanese factories struggled to achieve, even in their best facilities, appeared to be standard throughout the American engine. Every cylinder was perfectly matched, every bearing surface finished to a mirror smoothness that reduced friction to absolute minimums. Yamamoto ran his fingers along the surface of a piston. It was so perfectly smooth that it felt almost slippery, despite being completely dry. He knew what this meant. The Americans had machined tools of a quality and precision that Japan could only dream of. These weren't hand-finished components carefully prepared by master craftsmen. This was mass production operating at a level of consistency that suggested computer-like precision, though of course such machines were still decades away. It meant that somewhere in America, factories were producing these engines by the hundreds, perhaps thousands, each one built to these exacting standards. The cooling system revealed another technological gap. The American engineers had designed an intricate network of passages within the cylinder heads that allowed for incredibly efficient heat dissipation. The Japanese team spent days mapping these passages, creating detailed drawings that showed the complex three-dimensional routing of coolant through the engine. It was a masterpiece of thermal engineering, allowing the engine to operate at higher temperatures and pressures than any Japanese power plant could safely sustain. Yoshiro Tanaka, the team's expert in thermodynamics, calculated the heat transfer rates and shook his head in disbelief. The Americans had achieved a cooling efficiency that was nearly 40% better than the best Japanese designs. This single advantage had cascading effects throughout the engine's performance envelope. It meant higher compression ratios, more aggressive timing, and ultimately more power from each cylinder. It also meant greater reliability, as the engine could operate within safe temperature ranges even under combat conditions that would cause a Japanese engine to overheat and fail. The supercharger system was perhaps the most sophisticated component of all. Japanese engineers had been working on supercharger technology for years, trying to give their fighters the high-altitude performance they desperately needed. But the two-stage, two-speed supercharger on the R2800 was in a different class entirely. It was a mechanical marvel that automatically adjusted itself to provide optimal boost across a wide range of altitudes. The team spent nearly a week just studying the supercharger's mechanism. The gearing was incredibly complex, with multiple planetary gear sets that allowed for seamless transitions between speed ranges. The quality of the bearings was exceptional, designed to handle the tremendous rotational speeds without wearing prematurely. Most impressive was the automatic control system that managed the transitions between supercharger speeds. It used a sophisticated mechanical computer, a system of cams and springs and pressure sensors that responded to altitude changes and throttle inputs with precision that bordered on the intuitive. Hiroshi Nakamura, who specialized in forced induction systems, attempted to sketch out how they might replicate this technology. After 3 days of calculations and drawings, he came to a sobering conclusion. They couldn't, not with current Japanese manufacturing capabilities. The precision required, the quality of the components, the complexity of the control systems, it was all beyond their current reach. They could understand the principles. They could see how it worked. But translating that understanding into production was another matter entirely. As the weeks of examination turned into months, a comprehensive picture emerged that was far more troubling than anyone had anticipated. The Pratt & Whitney R2800 wasn't just a better engine than what Japan was producing. It represented a completely different approach to aeronautical engineering, one backed by an industrial infrastructure that was simply in a different league. The American philosophy was clear in every component. They had designed for reliability and ease of maintenance, not just performance. Parts were standardized and interchangeable. Maintenance procedures were simplified through clever design choices. The engine could be partially disassembled and serviced in the field with relative ease. Japanese engines, by contrast, were often temperamental machines that required highly skilled mechanics and frequent attention. One evening, as the team worked late under harsh fluorescent lights, Yamamoto gathered his senior engineers for a frank discussion. They had been documenting their findings in detailed reports that would eventually make their way to the highest levels of military and industrial leadership. But before those reports were finalized, Yamamoto wanted to hear his team's honest assessments, away from the official record. What emerged was a consensus that was as unanimous as it was disturbing. The Americans were not just ahead in engine technology, they were ahead in fundamental industrial capacity. The R2800 could only exist because America possessed advanced machine tools, sophisticated metallurgy, reliable quality control, and abundant resources. These weren't things that could be quickly copied or easily acquired. They represented decades of industrial development and massive capital investment. Sato, the metallurgist, was particularly blunt. He had finally identified most of the alloys used in the engine. Some required elements that Japan simply didn't have access to in sufficient quantities. Others required refining processes that needed equipment Japan couldn't build and couldn't import through the Allied blockade. Even if they could somehow obtain the raw materials, training the workforce to use them properly would take years. Tanaka added his own grim assessment. The Americans were clearly not resource-constrained in the way Japan was. The engine used materials lavishly, without the constant weight-saving compromises that characterized Japanese design. This wasn't wasteful engineering. It was engineering freed from the desperate resource scarcity that plagued every Japanese design project. The Americans could afford to build heavy, robust engines because they had the materials to do so and the powerful aircraft to carry them. The team also discovered evidence of something that troubled them even more than the technical gaps. As they examined the engine's serial numbers and manufacturing stamps, they could trace its production history. This particular engine had been built in a factory in Connecticut, but the stamps and codes revealed something else. This was not a prototype or a limited production run. This was a standard production engine, one of thousands being manufactured simultaneously in multiple factories across America. Intelligence reports had suggested that American industrial output was substantial, but seeing the evidence firsthand was different. The precision and quality of this engine meant that American factories were churning out these technological marvels at a rate that Japan could never hope to match. For every engine Japan produced, America was producing 10, 20, perhaps even more, and each American engine was superior in nearly every measurable way. Yamamoto found himself thinking about the pilots, the young men who climbed into their cockpits each day and flew against these machines. They were brave, skilled, and dedicated. But bravery could not overcome a several hundred horsepower deficit. Skill could not compensate for an aircraft that was structurally stronger and faster. The technological gap was translating into a mortality gap, and there was nothing that courage or tactical brilliance could do to close it. The examination also revealed American approaches to manufacturing that were almost philosophical in their differences from Japanese methods. Where Japanese engineers pursued elegant simplicity and minimal weight, American engineers embraced robust over-engineering. Components were designed with safety margins that seemed excessive by Japanese standards, but those margins meant American engines could tolerate battle damage, poor maintenance, and harsh operating conditions that would destroy a more delicate Japanese power plant. This philosophy extended to the training and skill requirements for pilots and mechanics. The R-2800 was designed to be operated by average pilots and maintained by adequately trained mechanics. It had built-in tolerances for human error. Japanese engines, by contrast, required experienced pilots who understood their quirks and limitations, and master mechanics who could coax optimal performance from temperamental machines. In a long war of attrition, the American approach had obvious advantages. The fuel system revealed yet another disparity. The engine was designed to run on high-octane aviation gasoline, 100 octane or better. Japan's refineries were struggling to produce fuel that met even 87 octane standards consistently. The higher octane fuel allowed for higher compression ratios and more aggressive engine timing, both of which contributed to the R-2800's impressive power output. Even if Japan could somehow replicate the engine design, they lacked the fuel to run it at its designed performance levels. One of the younger engineers, a man named Kenji Watanabe, who had joined the team halfway through the examination, made an observation that stuck with Yamamoto. Watanabe pointed out that every challenge they were identifying had a common thread. America's advantages were not primarily about individual genius or brilliant innovation. They were about systems, infrastructure, and industrial maturity. Individual Japanese engineers were every bit as capable as their American counterparts, but those American engineers were working within an industrial ecosystem that magnified their efforts, while Japanese engineers were constantly fighting against resource constraints and industrial limitations. As spring turned to summer in 1944, the team completed their examination and began compiling their final report. The documents they produced were exhaustive, running to hundreds of pages of technical drawings, metallurgical analyses, performance calculations, and manufacturing assessments. But the core message could be summed up in a single, devastating sentence. Japan was fighting an enemy whose industrial and technological capabilities were years, perhaps even a decade, ahead of their own. The reports made their way through the bureaucratic channels, reaching the desks of military planners and industrial leaders. The reactions varied from denial to despair. Some officials insisted that Japanese fighting spirit and tactical innovation could overcome material disadvantages. Others recognized the reports as confirmation of what they had privately feared, that Japan had entered a war it lacked the industrial capacity to win. There were attempts to apply the lessons learned from the Corsair engine. Nakajima and other manufacturers tried to incorporate some of the design principles into new engine projects, but the gulf between understanding a technology and being able to produce it proved insurmountable. The advanced alloys couldn't be replicated. The precision manufacturing techniques required tools Japan didn't possess. The cooling systems were too complex for existing production facilities. Some incremental improvements were made. Japanese engineers applied what they learned about cooling efficiency to modestly improve existing designs. Supercharger technology received renewed attention and saw some advances. Quality control procedures were tightened in an attempt to achieve more consistent production standards, but these were marginal gains that did little to close close the fundamental gap. What made the situation even more frustrating was that Japanese engineers could clearly see the path forward. They understood the theoretical principles. They knew what needed to be done, but knowing and doing were separated by an industrial chasm that couldn't be crossed quickly, and certainly not while fighting a total war that was consuming resources faster than they could be produced. Yamamoto, in particular, struggled with the implications of what they had discovered. He had devoted his career to Japanese aeronautical engineering, and he was proud of what his nation had accomplished. The Zero had been, for a time, the finest carrier fighter in the world. Japanese engines had powered aircraft that had struck Pearl Harbor and ranged across the Pacific with impunity. But that time had passed, and the examination of the R-2800 had shown him exactly why. In quiet moments, he thought about the different paths that had led to this moment. America had spent the decades before the war building an industrial base of unprecedented scale and sophistication. They had invested in education, research, infrastructure, and manufacturing capacity. They had developed a culture of mass production that emphasized consistency and quality at scale. Japan, despite its rapid modernization, had never achieved that same industrial depth. Its economy was more fragile, its resource base more limited, its industrial traditions still evolving. The war in the Pacific ground on through 1944 and into 1945. American aircraft, powered by engines like the R-2800, dominated the skies with increasing authority. Japanese pilots, flying in aircraft that were outclassed and increasingly obsolete, fought with desperate courage against impossible odds. Production of Japanese aircraft actually increased in the final year of the war, but the planes being produced were inferior to what the Allies were fielding, and the quality was declining as resources grew scarce and experienced workers were drafted into other services. The team that had examined the Corsair engine was eventually disbanded. Some of the engineers were reassigned to other projects. Others found themselves drafted into increasingly desperate military research programs. Yamamoto remained at Nakajima, working on engine refinements that he knew would make little difference to the war's outcome. He watched as the strategic situation deteriorated, as American forces drew closer to the Japanese homeland, as the cities burned under incendiary raids carried out by bombers powered by the same advanced technology he had studied. The examination of the R-2800 had been both an educational experience and a moment of truth. It had provided invaluable technical knowledge and had simultaneously revealed the futility of trying to close a technological gap that was measured in years of industrial development. The Japanese engineers had approached the captured engine with professional curiosity and national pride. They had left the examination with a profound understanding of the industrial realities that were shaping the war's outcome. Years later, after the war had ended and Japan had begun its long process of reconstruction and reindustrialization, some of the engineers who had participated in the examination would reflect on what they had learned. The technical knowledge was valuable and would contribute to Japan's post-war aeronautical industry, but the broader lesson was more important. Industrial capacity was not just about factories and machines. It was about infrastructure, education, research, resource management, and 1,000 other factors that had to develop together over time. The post-war Japanese aviation industry would eventually become one of the world's most sophisticated, producing engines and aircraft components that met the highest international standards. Engineers who had examined the R-2800 would play roles in that development, applying lessons they had learned during those intense months of study. But they would do so within a very different context, one of international cooperation rather than isolated development, of access to global resources rather than desperate scarcity. The story of the captured Corsair engine is ultimately a story about the nature of technological competition between nations. It illustrates how innovation and engineering excellence are necessary but not sufficient for technological leadership. They must be supported by robust industrial systems, adequate resources, and the time to develop mature manufacturing capabilities. Japan's engineers were every bit as intelligent and dedicated as their American counterparts, but they were working within a system that could not provide them with the tools and resources they needed to compete on equal terms. The examination also highlighted the cumulative nature of industrial advantage. Each American technological edge, better materials, more precise machining, more efficient cooling, more sophisticated fuel, built upon the others to create a compound advantage that was far greater than the sum of its parts. Closing one gap would not be enough. All the gaps had to be addressed simultaneously, and that required an industrial transformation that couldn't happen during wartime. For the men who had spent months carefully documenting every detail of the Pratt & Whitney R2800, the experience was both humbling and educational. They had approached the task with professional pride, confident in their own expertise. They had left it with a much clearer understanding of the challenges their nation faced and a sobering appreciation for the industrial might they were confronting. The engine itself, that massive 18-cylinder radial that had traveled from a jungle airstrip to a research facility outside Tokyo, eventually disappeared into history. Some components were probably retained for continued study or display. Others may have been recycled as Japan's industrial situation became increasingly desperate in the final months of the war. But the knowledge it provided, the lessons it taught, and the sobering reality it revealed continued to resonate long after the war had ended. In the broader sweep of World War II history, the story of Japanese engineers examining a captured American engine might seem like a footnote, but it encapsulates something fundamental about the nature of the conflict. The Pacific War was decided not just by strategy and courage, but by industrial capacity and technological superiority. The side that could produce better weapons in greater quantities, that could equip its forces with reliable, high-performance equipment, and that could sustain that production throughout a long conflict, held decisive advantages. The examination of the Corsair engine gave Japanese engineers a clear view of exactly how large those advantages were. They saw American industrial excellence literally taken apart piece by piece, measured, analyzed, and documented. They understood, perhaps better than anyone else in Japan at that time, exactly what they were up against, and they knew with the certainty that comes from detailed technical analysis that courage and tactical skill could not overcome the fundamental industrial disparities that characterized the Pacific War. Today, the F-4U Corsair is remembered as one of the finest fighters of World War II, a powerful and distinctive aircraft that excelled in both air-to-air combat and ground attack roles. The R2800 engine that powered it is recognized as a masterpiece of aviation engineering, one of the most successful and longest-lived aircraft engines ever produced. More than 125,000 R2800s were manufactured, and variants of the engine continued in service for decades after the war ended. But for a small group of Japanese engineers working in a research facility outside Tokyo in 1944, one particular R2800 represented something more than engineering excellence. It was a mirror that reflected the industrial realities of the war, a teacher that revealed uncomfortable truths about the technological balance of power, and a symbol of the challenges that Japan faced in its attempt to fight a sustained industrial conflict against an opponent whose manufacturing capabilities were simply overwhelming. The men who examined that engine did their duty with professionalism and dedication. They learned everything they could from the opportunity they had been given. They documented their findings thoroughly and honestly, even when those findings were discouraging. They tried to apply what they learned to improve Japanese aviation technology, but in the end, they were fighting against fundamental industrial disparities that had developed over decades and could not be reversed in months or even years. Their story is a reminder that war is not just about tactics and courage, but about the industrial and technological foundations that enable military force. It is about the unglamorous work of building manufacturing capacity, developing materials science, training skilled workers, and creating the infrastructure that allows innovation to be translated into production. The Japanese engineers understood their craft brilliantly. What they learned from the Corsair engine was that craft alone was not enough. In modern industrial warfare, victory required a complete ecosystem of capabilities, and building that ecosystem was a task measured in decades, not months. As the tropical sun set on another day in the Pacific War, and as engineers in Tokyo continued their meticulous examination of an American engine, the truth was becoming clearer. Japan had entered a contest that required not just courage and tactical brilliance, but industrial depth and technological breadth that it did not possess. The Corsair engine was not just a machine, it was evidence, concrete and irrefutable, of the industrial revolution that America had undergone and Japan had not yet completed. Understanding that truth was valuable, but it came too late to change the outcome of the war that understanding would have required years of preparation to prevent. The examination of the captured Corsair engine stands as one of the most thorough and honest technical assessments conducted during the Pacific War. It was an education in excellence, delivered through disassembly and measurement that showed exactly how far Japan had to go to match American industrial capabilities. For the engineers who conducted that examination, it was both their finest work and their most sobering revelation. They had looked into the heart of American aviation technology and seen the future of their profession. That future would eventually arrive, but only after a war had been lost and a nation rebuilt.